Before I get started today, I have a question for you. What is the world's largest man-made thing? Any ideas? Well, the correct answer is actually the Great Pacific Garbage Patch, with a surface area of 1.6 million square kilometers. That's nearly 6 times the size of New Zealand, made up of 80,000 tons of plastic. Yep, that's right. It's the biggest thing that humans have ever created. Quite poetic, isn't it? According to Plastics New Zealand, each New Zealander consumes approximately 31 kilograms of plastic packaging every single year, but only recycles 5.58 kilograms. Furthermore, plastic accounts for around 8% of New Zealand's waste by weight. However, because plastic is so light, it's estimated to take as much as 20% of our landfill space. Around 252,000 tons of plastic heads to our landfills every single year. Furthermore, lots of plastic actually ends up out in the wild, rather than heading to our recycling facilities or our managed landfills. So then, what currently happens to plastic out in the ocean? Larger plastics, like plastic bottles or plastic packaging, are broken down from sunlight, oxidation, friction, and animals nibbling away at the plastic. This process continues for smaller plastics until the plastic becomes nanoplastics, only visible under a microscope. These nanoplastics cannot be fully removed from the environment and are extremely harmful to marine life. If consumed, these nanoplastics get stuck in the digestive systems of living organisms and could even penetrate tissues and organs. The process of breaking down into nanoplastics can take up to 500 years for the standard plastic bottle. Even though the plastic has been broken down, it still exists in a harmful form as nanoplastics. Okay, so it's quite clear that plastic that ends up in landfills or in the ocean can have significant environmental harms, even when it is broken down. What about plastic, or more specifically, polyethylene terephthalate, PET, that is recycled? In our current recycling techniques, the plastic is first shredded into smaller pieces, making it easier to clean and process. The plastic bits are then washed and cleaned in order to remove labels, glue, and residue. Next, the plastic pieces are grinded up into small flakes. At this stage, the smaller flakes, called rPET or recycled plastic flakes. These recycled flakes are then tested for quality and safety and made into new plastic items. Note that this process is not particularly profitable, and only a small proportion of plastic can even be recycled this way. Furthermore, in many countries, like New Zealand, labor is so expensive that it isn't even done here. This means that it's not a viable or economic solution for dealing with the plastic waste crisis. Clearly, we need a better solution, one that is more sustainable, one that is more thorough, and one that is more reliable. Polyethylene terephthalate, or PET, is the most common type of plastic, and it is a polymer, a long chain of monomer building blocks. PET biodegradation is an up-and-coming field where scientists are trying to find and build enzymes that can efficiently break down these polymers back into the monomer building blocks. Doing this would essentially allow us to perfectly recycle PET plastics at a molecular level. This process is called depolymerization, and when we can find an efficient and cheap way to do this, we can say goodbye to plastic waste forever, as we can simply depolymerize used plastics and turn them into any other plastic thing that we like. In 2016, several Japanese scientists discovered a bacteria named Ideonella sulcanesis 201F6, found out in the wild in a plastic recycling facility, nibbling away at the delicious PET. The bacteria uses a two-enzyme system to depolymerize PET into its building block parts, PET hydrolase and MHET hydrolase, known as PETase and MHETase. Let's take a look at how it works now. Essentially, the bacteria utilizes PETase to break down PET into BHET, MHET, and TPA. Then, the PETase further breaks down the BHET into MHET and EG. Finally, the MHET is broken down into TPA and EG. TPA and EG happen to be the origin monomer building blocks for PET. That is to say, we can use TPA and EG to synthesize PET in the first place. This means that once we have depolymerized PET in TPA and EG, we can use these building blocks to synthesize plastic again, and this could be made into any new thing that we like. Okay, so that's the plastic enzymes part of mutant plastic ninja enzymes. Let's now talk about the mutant part. Scientists have found a way to modify the structure of PETase to make it more efficient. By narrowing the binding cleft of the enzyme, or the active site, PET takes just a few days to break down the PETase to break down the PET, as compared to hundreds of years in oceans. This is great. Furthermore, scientists have found a way to make super enzyme chains. By stitching together PETase and MHETase enzymes into long chains, we can again increase the efficiency of the PET degradation. This is because the dual action of the two enzymes is amplified when in the chain formation. Interestingly, just last year, in 2020, scientists discovered another enzyme with similar action that was able to break down PET in just 10 hours and at 72 degrees Celsius as well. This enzyme is called leaf branch composite cutinase, or LCC, and was found to be at least 33 times more efficient than all the other enzymes that have been tested before. LCC uses a similar enzymatic pathway as ideonyl cell kinesis, but it is much more thermostable, meaning that the enzyme is much less likely to denature or lose efficacy over time. This is an incredible advancement and is already being trialed in industry. This is all great and means that the solution is scientifically viable. However, we need to also make sure that it is economically and socially viable. Firstly, there is a challenge surrounding the cost of mass producing the necessary bacteria. Just like for many other bacteria solutions, there exist many different ways for which such enzymes can be economically mass produced. This will not be a difficult obstacle to overcome for scientists. Another concern could be the quality of the recycled material. However, in this case, the recycled material is recycled at a molecular level, meaning that it would be indistinguishable from brand new plastic. There is also an opportunity cost to recycling plastic. It will be likely be much cheaper to produce new plastics rather than recycle old plastics. For this reason, government intervention, such as subsidies or taxes, may be necessary to ensure that this technology is appropriately utilized. It is also possible that this technology has unforeseen ecological impacts. It is yet to be seen whether the production process of the enzymes or if the recycling process itself could potentially have harmful byproducts. It is also possible that if the enzymes leach into the environment, they could damage ecosystems. This also brings into question the public perception of this technology and whether consumers would be willing to utilize recycled plastic products. Some consumers may see recycled products as inferior and therefore not be willing to purchase them, even if they are subsidized. Equally, there may be an appeal to certain consumers to purchase these recycled items. I just want to end by talking about an important perspective in this conversation about strategies to protect the environment. Firstly, this solution acknowledges the fact that we are tightly interconnected with nature. The fact that a seemingly random bacteria is capable of recycling and digesting this pernicious polymer that humans have created represents this. Inspired by nature, we're able to harness the power of naturally occurring organisms to help us solve the problems that we've created. Secondly, this solution is sustainable. By using these enzymes to recycle PET polymers, we can one day achieve our dream of a plastic waste-free future. It's not completely viable to abolish plastics altogether, but this technology just means that plastic is no longer considered permanent waste.